Welcome everyone, and thank you for joining us today. Today's webinar is presented by Sports Field Management Association. This is the second week of our series of post-conference education. Our featured speaker today is Dr. Bryan Hopkins, professor at Brigham Young University. Today, he will be presenting Irrigating with Reuse Water and Managing Salts and pH. Attendees will be muted during the presentation. If you have any questions, please type them into the Q&A feature and they will be answered at the end of the presentation. Thank you for joining us today. You can go ahead and get started.
Thank you. It's an honor to be asked to speak, and important topic here. More and more of us are needing to use recycled water or reuse water, and many of our water supplies on top of that are becoming more challenging in terms of salts and pH a little bit. I'm going to focus mostly on the salt side of this today. I acknowledge Tyler with SciScapes as helping me put some of this together. Let's see. There we go. So just background. I mean, it's part of why we're seeing more of this, as I said, is we're in a mega drought, and this thing is bad. It's as bad as it's been in hundreds of years. Go to NASA's website, for example, right here. You can kind of read about it. You read about it all over the place. And it's not just the West. We see it out other places too. Lake Powell, which is south of us here in Utah, is just in a crisis, which is, we got huge water supply issues that could be a real problem if that lake dries up. We got a lot of folks in a lot of trouble. Just here in Utah, where I'm at, just about 30 miles north of me, and a little bit to the west is the Great Salt Lake. We about 3 dozen scientists and some others got together here a couple of weeks ago and issued an emergency briefing, because the Great Salt Lake, if we continue on the rate that we're on, it's going to be dry in 5 years, which would be an ecological disaster. I don't have time to explain why, but it would be bad. And thankfully, we've had a really good snowpack this winter, and so maybe that slows that down. But it's certainly a concern. It's something we're all thinking about in this whole mega drought. It's mostly in the West, as you can imagine, but it does affect other places. Back in 2012, I had a bunch of folks I was working with down in the Atlanta, Georgia area, and it was a really rough drought. So it's not just the Western United States that can be hit, but it can be other areas too. So what's the knee-jerk reaction? Everybody wants to get rid of the grass, and I just really don't like that idea. I think it's important that we understand the benefits of grass. And we, as turfgrass professionals, we need to be better at communicating that the grass can be important. Now, I'm the first one to say that maybe we ought to cut back on the grass. My house, for example, I have less grass than anybody in my neighborhood. I have enough that my front lawn doesn't look stupid. I have reasonable property values. My neighbors aren't mad at me for having an ugly yard. I also have grass in my backyard a little bit around my trampoline so my grandkids can play, but most of the rest of it is a water-wise landscape. So I admit that, but getting rid of sports fields, for example, would be terrible. I mean, it's just as an important part of the health of individuals and society. So we need to be better at communicating those things. We could be better stewards of the earth, though. We can do this and simultaneously have beautiful functional landscapes. But one of those issues is what our topic for today is, like, okay, if we're going to be using recycled water in an effort to try to conserve water, and as well as costs, for our facilities, sometimes that can be a savings for us. How do we do that? I think one little point here I wanted to bring up before I really dive into the meat of this is, I think it's important to have good public relations in all of this. We need to show how we're being good stewards. Like I've seen several properties that I've been on that are using reused water, and they've got signage out so that people are coming by and saying, "Oh, that's good to know." They're trying to be conservation minded. So I think that's important. All right, let's dive into things. First of all, a couple of things. No, number one, if you don't get anything else out of this, I hope you understand what I'm about ready to say, because I run into this all the time. I go to meetings and I hear even scientists that don't understand the difference between salinity and sodicity. Sodium is a salt, and it does contribute to salinity, but it can be a problem in and of itself. In other words, I can have a sodic soil that's a sodium affected soil that does not have an overall salt problem. And vice versa. I can have a salinity problem that doesn't necessarily have a sodium problem. We can also have the combination of the two. So those are two separate issues, and they need to be understood separately, and we need to communicate about them separately. So that's important. We're going to come back to that and talk about each one. Just also by way of background here, just to kind of get an idea, one way of expressing salts is TDS, which is total dissolved solids. I don't usually express it that way, but just from percentage standpoint, it's kind of interesting to look at this. So fresh water's got pretty low salts that are dissolved. So the salts are actually dissolved in the water. If you took a teaspoon of table salt and put it in a cup of water, you stir it up, it would dissolve, right? I mean, it's actually, breaking apart the salts, and they're going into solution. So that's what we're talking about. If we look at brackish water, it might be up to 3% TDS. Saline water is up to 5%. Brine is considered more than 5%. So if you kind of look at some of the saltier places on the earth, the ocean's about 3.5. It's classified as a saline water. The Great Salt Lake, which I was just talking about, is actually a brine. It's roughly 6 times more salty than the ocean. And then like the Dead Sea, similar, is also very salty, saltier than the ocean. Now, where do these salts come from? Well, when precip, snow or rain hits the soil surface, it moves into and through and over that soil, and guess what? Any salts that are there potentially can dissolve and be carried with the water. So as it's moving across the landscape and down through the aquifers, it's picking up salts as it's going along. And eventually, in most places, those salts end up in the ocean, which is why the ocean's so salty. So the sun dissolves the water, the salts are left behind, and therefore we get these salt water bodies. The reason why the Great Salt Lake and the Dead Sea and others are salty is that there's no outlet. We live in what we call an endorheic basin here in Utah, which is more than just Utah, by the way, but the water that falls here in Provo, Utah, it doesn't make it to the ocean. It's kind of landlocked, so to speak, and the water ends up in there, and that gets salty. So that's how it gets salty. So that's also relevant for irrigation water, right? Because if you pass the water through the soil, it's picking up some salts, and so reuse water is higher salts than the initial irrigation water that went through. So that's an important thing to realize. When we talk about soil salinity, again, salinity, salts are synonymous. These salts are characterized by an ionic bond between cations and anions. And I know this, maybe you don't want a chemistry lesson, but I think if you understand a little bit of chemistry, at least rudimentary, I think it helps you be a better manager. So sodium is what we call a cation. It's got one positive charge. It's an atom that's got a positive charge. Chloride has got one negative charge, and they like to connect together, and their electrical charge cancels each other out. So common cations, and you'll recognize these. Potassium is K. That's a fertilizer. Calcium is very common in our soils and in our waters. Magnesium too, and then sodium, of course. These are the main base cations that are in soil. So if you were to measure all the cations in your soil, most of our soils, these are the main bases that are there. Anions are things like sulfate, chloride, bicarbonate, and carbonate. Those are kind of the main anions that we find in our soils as well as our irrigation waters. So those are the salts we're talking about. Now you can connect any one of those. Like I can connect potassium and chloride. I can connect, sodium chloride. I mean, so you pick one of the cations and pick one of those anions and they'll match up. Now, obviously, if there's two charges, like sulfate, if I'm going to add that to potassium, I got to have two potassiums because they're only one charge. So the charges have to kind of balance out. But that's just kind of simple math. 1 + 1 = 2. So when we start looking at common salts, sodium chloride, of course, is table salt. We all are familiar with that. Ammonium nitrate, ammonium sulfate, urea, potassium chloride, potassium sulfate, calcium sulfate, which is gypsum, and calcium carbonate, which is limestone. You recognize those as our most common fertilizers. All fertilizers are salts. Some are, like you'll notice, I didn't include any of the phosphorus fertilizers. They are salts, but they're not soluble salts. They're not very soluble. So the soluble salts are really the ones that just kind of stay in the soil solution and sort of causes more problems. So these are the ones that are very common. I have some frustration sometimes when, again, if you want to pick a thing that is very commonly misunderstood in our industry, is that, hey, let's add gypsum to my salty soil and it's going to fix it. No, it's not going to fix it. Why would you add a salt to a salt problem? That doesn't make any sense at all. Now, gypsum is important for sodic soils, and we'll talk about that more in a minute. So that's a different deal, though. But if I have a salt problem, then don't add more salt to a salt problem. Now, we still need some fertilizer, right? I mean, we can't just stop fertilizing, but we should be careful not to over fertilize too, because those, again, they're salts, and we need them. Everybody needs salt. You need salt. I need salt. Plants need salts. They're good, but too much is bad. And too much, what that does to you, like if you were to go drink a gallon of water out of the Great Salt Lake, you'd be dead. And what happens is the salts would pull all the moisture out of your cells and you would desiccate. So that's what happens. I have a hydroponic growth chamber here at BYU. And we grow plants in there, and the roots are literally floating in water. But if I add enough salt, I can cause those plants to die from desiccation, even though they're just, water everywhere, not a drop to drink. It's just floating in water, but they can't take it up because the salts are have an affinity for that water and they won't let the plants take it. So here's some things in terms of water. And I know that's a lot. We're not going to really read through all that, but just here's some various salts that commonly are in the water. Some are more common than others, like sodium and chloride and sulfate. Those are pretty common in our irrigation waters. So definition of salt, I mean, this is the chemistry definition of it, is, these ionic compounds that result from the neutralization of an acid and a base. There will be no quiz after this, so you don't need to worry about memorizing that, but just to put it out there. So again, positive cations and negative anions, those things join up together. So in solid form, these salts are crystals, like what's in your salt shaker, right? But when we put it in liquid form, they separate. And so I just have these sodiums and calciums and potassiums floating around, and chlorides there too. They're not joined together when they're in liquid form, when they're in the irrigation water. So my anions, these are my common anions. I've listed a few more here than what I showed before. These are things that we can find in water. There's others too, but these are really the ones we measure and are concerned about sometimes. The cations, again, this is showing a few more than what I showed before, like zinc, for example. Yeah, it's a cation. It's kind of like phosphorus, though. It's not really super soluble, so we don't really worry about it too much in terms of a salt salinity issue. So again, is that good or bad? Salts are essential for life, as I mentioned. Got to have them. When I'm teaching this to my students, I bring out this plate of what they often think is brownies. I have it sitting up on the table, and they're looking at it and they think it's some powder sugar coated dessert. I've never had anybody actually take a bite out of it, but it's been close a couple of times. This is not. This is a soil, and it's derived from a manco shell. which is found in places in Utah and other places in the world too. So that's the rock itself. But once it becomes exposed to the surface of the earth and starts getting weathered, it really quickly turns to this. It breaks apart. There's a lot of salts inside of that shale, that rock. And those salts, with evaporation, they can end up on the soil surface, just like this here. So so when it's really bad, you can literally see the salt on the surface. Now, we don't want that to happen. If we're letting that happen, we're going to have dead grass. So we're not wanting that. But I like to show that picture just to visualize it. Again, salts have a great affinity for water, and that's what happens. They reduce the amount of water that's taken up by plants. You'll notice these are the salt flats. If any of you were here last week or a couple weeks ago for the SFMA meeting, I don't know if you had a chance, but if you ever get back to Salt Lake, you should drive out there. It's really interesting. And these are super flat, just almost like they were made that way, with all these salts dissolving over the centuries. And so they do a lot of races out there because it's, they can, all the land speed records are set out there because it's just this big flat area. What you don't see are plants, none. And that's not because anybody's spraying herbicide. It's because those salts are going to not allow plants to grow when they're in those kinds of concentrations. We see it in other places too, especially in the West. You can drive by and see some spots where you get these accumulations of salts. So, again, what causes it? So again, TDS and electrical conductivity are how we measure it. Why would we measure it with electrical conductivity? Well, if you were in the bathtub with pure water with no salts in it, and dropped your phone with your charger connected to the power, you'd be probably okay. Now, don't try that. But if you had just your normal bath water that's got salts in it, those salts are what conducts the electricity. And if you dropped a powered appliance in there, you would potentially die because of that, because those salts conduct the electricity, not the water. So anyway, we use electrical conductivity to measure these salts sometimes. That's important to realize. Now, so what happens? These salts can accumulate through evaporation. If you're putting on less water, so like here in this picture, we're not getting much rainfall. It's dry in the West, and so we have more evaporation than we have precip. So like out on the out by the Great Salt Lake, for example, we might get 12 inches of rain a year, and the evaporation is more like double that or more. So the salts they're soluble and they're moving up to the surface, and the water dissolves and the salts get left behind. So that's one way to accumulate them. We do get places near water bodies. So like there are some places near the oceans where you get some sea spray that can cause some problems. We get some salt dust movement, especially with dry salt lake beds, which is one of our concerns with the Great Salt Lake. And then the last one, which is our topic today, is when I do water reapplication. Those salts, plants are taking up the water. There's some evaporation, and some of the salts get taken up by the plants, but not all of them. And we can accumulate those salts in the irrigation water. Now, I'm showing you this. I know this is not turf grass, but to be honest with you, most of the research that's done in the world on salts and fertilizers too, actually, is in agriculture. And I'm just showing you this because we tend to have these values that we apply. Like, for example, if a soil is above 4.0 decisiemens per meter, which is this number, I don't know if you can see my mouse or not, but this DS/M, or millimoles per centimeter, we express electrical conductivity in those units. So if it's above 4, it's technically a saline soil. With turf grass and many other things, though, we get problems before it gets to 4, before it's that salty. And you can see that here too. So barley and wheat, which are grasses actually, they are actually fairly tolerant. Sugar beet, is pretty tolerant. Some other things are less tolerant, like beans and onions down there at the bottom of the list. Grasses have some differences as well. We have, typically our bluegrasses are the most sensitive to salts. So that's one option that you ought to be thinking about if you're going to be using reused water and or you have just salty water anyway. Bluegrass is not always the best choice. You'll notice on the other end of the spectrum, Bermuda grass can handle quite a bit more, and tolerate it. It doesn't necessarily like it, but it'll tolerate it, and some other grasses here as well. So we do get some differences here when the grasses too. Now, this says less than 3. Kind of depends on who you're talking to. I tell people that's a little too high for my comfort level. Ideally, I would like my electrical conductivity to be about less than 1.5 or even less than 1. If you're less than 1 decisiemens per meter, you're okay. You don't have a salt issue. When you start climbing above 1, and then potentially you're starting to get into trouble. Again, and some species are going to be more likely to be in trouble than others. By the time you get to 3 in turf grass with the bluegrasses, you're pretty much in trouble. And then I usually tell people I don't want to be above 3, even if I got Bermuda grass. So again, it'll tolerate really high levels, but is it going to give you a really great surface like you need in a sports field? No, it's not. And so you probably shouldn't be going too far with this table and saying, okay, we can take it up to 10. I would not recommend that unless I absolutely had to. And then if you do, you may want to give me a call and we'll talk it through a little bit. So in some cases now, I'm going to kind of shift gears on you a little bit. The overall salts aren't a problem, but specific salts are high and causing a problem. So I already alluded to the sodium thing. Again, I can have a sodium problem even when my salts aren't high. We can also run into others like chloride or boron. They can be toxic as well. They're also salts, and they can become toxic. Here are some sodic soils. I was in my son there was in the Marines in Okinawa, Japan, and I spent a month over there with them. And I'm walking along. This is actually alongside the ocean, and in a place where it rains a lot, where we don't usually see these saline and sodic soils in high rainfall areas, but it can happen, especially near the ocean. And that's what's happening here. This is right next to the ocean, and we spotted these saline soils, or excuse me, sodic soils. So what's going on there? That soil is just destroyed, and you're going to have a really hard time moving water into that. You'll notice plants aren't growing because of the sodium issues. Here's a little bit closer up view of it. It's pretty cool for a soil scientist to see this. Not so cool if you're trying to grow plants. So what happens with sodicity is that we deflocculate the soil, which means that the soil aggregates break apart. So obviously, if you have a sand-based sports field, an ASTM spec sand-based sports field, or a USGA spec golf green or a tee box, you don't have aggregates. And so I'm not worried about this. This is for my native fields where I have soil aggregates, and they're an important part of what we're doing. So what can happen though is that sodium gets so high, and not concentration, by the way, it's the percentage is what's important. And I'll show you that here in just a minute, but it can break apart those aggregates. And again, if you look back up here, that's what's happened. It's broken them apart. And now we just have this destroyed soil. It can also be a problem below the soil surface. This is more common in higher rainfall areas. You can find some places where there's what we call a natric horizon, where sodium is accumulating in the surface or the subsurface and forming a destroyed layer down there that water won't move through very well. So that's worth talking about. Again, I've mentioned sodium chloride and boron, which are kind of the main ones we're interested in. I'll talk about mostly today, but some of these others can also be in water, and they could potentially be a problem, but pretty rare. So let's talk about sodium toxicity now. So that's different than a sodic soil. So sodic soil, again, is the soil structure gets destroyed. A sodium toxicity means that the plant is actually sick because it's got too much sodium in it. Now, to be honest with you, I don't see that very often. It's not easily diagnosed, for one thing. And usually, like it says here, is we precede it with sodicity, which means, that the soil kind of destroys before the plant gets sick. And then if the soil gets destroyed, potentially have water issues, right? Water won't go into the soil. So now it's a water. So both salinity and sodicity are really related to water problems. So now these are often corrected with gypsum. I'm not a big fan of calcium nitrate because you're just really adding up a lot of nitrogen there that you probably don't want. So gypsum is the calcium sulfate. That's typically what we do. And I'll show you another slide here in a minute that's got the management on it. But if I do have too much sodium, these are kind of the symptoms that you can see. Chloride toxicity, this is fairly common actually in irrigation water. And a lot of people just aren't tuned into it. They don't even realize what's happening. They think they've got a salinity issue when in fact they have a chloride toxicity. And again, chloride's a salt, and chloride does contribute to salinity, but you can have low salts but still have a chloride toxicity. So just keep that in mind. Chloride, it can really accumulate on plant leaves. It can really cause a problem. The good news is it's easily leached, and it's solved basically in the same way we solve salt problems, which we'll show here in a minute. So here's some symptoms. To be honest with you, it's visually difficult to identify it. Usually you need to be analyzing your soil, analyze your water, and analyze your plants. And if you'll do those things, that will help us diagnose it. Boron toxicity is similar. There's one thing, so chloride and most of the other nutrients, and by the way, chloride's a nutrient, right? So I got to have some of it. Just too much is bad. Boron's a nutrient, but too much is bad. There's usually, for most of the nutrients, a pretty wide range of what the soil can have between, where something is deficient, something's toxic. Boron is like copper, actually. Those two are really notorious. There's a pretty narrow range of sufficiency. So, and I've seen this. I've actually seen boron toxicity from fertilizer application when somebody goes out and accidentally puts on too much boron, and anyway, they can kill their plants. But we can also get it from the irrigation water. Certain irrigation waters are high in boron. Many are not, but some are. So it's important to test your water. That's a major take-home point from today. Test your water. Usually this is coming from wells or springs that are high and naturally high in boron. And again, these are some symptoms. Visually, you can see it, but I would recommend doing soil, water, and tissue testing. So it's important to measure, and not just the water. You need to measure the soils. We need to look at the salt and sodium concentrations. Most soil test labs are not providing chloride and not providing boron. Some will provide boron, but it's, in many cases, if you want those, you're going to have to ask for them. I typically am asking for boron, especially on sand-based fields, because it's commonly deficient. I don't usually ask for chloride unless I kind of suspect I have a problem. And usually I'll look at that with my water. So it's important to have your water analyzed. And then I also do tissue testing, especially on high-profile fields. I think it's important to do that. I don't have time today, only in an hour, to cover everything. I'm happy to sit down with anybody and kind of talk that through a little bit if you want to know how to manage doing these measurements. We're going to do a little bit today. Here's one lab that, they've got some different things on here. You'll notice here the pH. So one thing a lot of people get really uptight about, especially in the West, is these high pH values. And they think, oh, I gotta put on something and lower it. And then they're like, I'm going to put on gypsum. And I know that there's people on this in this webinar who have done that or have recommended that. And it's just wrong. It's not correct. The only time I need to add gypsum is when I have a sodic soil. Now, the interesting thing is that a sodic soil, the pH will kind of bump high. It'll get up above 8.5 sometimes, oftentimes. And so adding gypsum will actually lower the pH. But the pH wasn't really the problem. The sodium was the problem. And the pH is just kind of going along for the ride. I'm looking out my window right now at the beautiful BYU campus. We have a gorgeous campus, and our pHs are all 7.8 to 8.4. Plants, many plants are adapted to these conditions, and they do just fine. We do not need to be spending time trying to lower our pH of our soil. If you have a sodic problem, treat the sodium, and then the pH will follow. But otherwise, unless you're growing blueberries or rhododendrons or other plants that require acidity, just, don't worry about it. And same thing with the water here. I'm not worried that pH is 8.5. It's alkaline. It does affect the availability of nutrients. So I have to manage my nutrients. I have to, typically I'm going to have to, pay more attention to phosphorus and zinc, iron, manganese, copper, boron. So I have to be aware of those things, and that's a topic for another day. You don't have time to cover all that right now, but it's just usually you're wasting your time trying to lower that pH because the soils are buffered and the water is buffered. And if you try to lower that pH, you're gonna have to add so much salt to get it done that you're gonna actually kill the plants. So let's not do that. I always hear another falsehood that's commonly perpetuated is acid forming fertilizers. Well, yeah, let's go put on ammonium sulfate. It is true that ammonium sulfate is an acid forming fertilizer, but the amount that we put on isn't even a drop in the bucket of what you need to change anything. There are literally thousands and thousands of pounds of salts out there, and adding a little bit of that is just not going to do much unless you've got a really unique situation. Like I'd work with some farmers up in Idaho and in the Columbia Basin up in Washington that have very sandy soils and kind of pure water. And over decades, their pHs have actually started to drop. So it does happen in some situations. So if you had a sand-based sports field and really kind of pure water, it could happen. I mean, you could do it, but that's kind of the exception and not really the rule. So I just wanted to mention that about pH. Now, if you have acid pH, we're probably a whole different environment. Typically in my acid soils that are in the high rainfall areas, I don't usually have salt problems, and I'm not usually having to use reuse water, or if I am using reuse water, it's probably not so salty that it's really a big problem. Now pH, if it's too low for many of our grasses, then yeah, it should be raised. And I add limestone to that, and limestone is a salt, but if I added it at recommended rates from a soil testing lab, you're going to be okay. You're not going to really drive your salt problems too high. Okay, I kind of went off on that, and now let's kind of focus back here on this thing. So you're going to see some different things on here, and I'm not going to have time to explain everything on a report like this, but like conductivity, again, that's electrical conductivity. Now they're showing it as millimos per centimeter instead of decisiemens per meter. They're equivalent numbers, so you can just interpret them the same, but you'll notice this guy, pretty low. It's less than 1, no salt problem. We're good. We're going to talk about the sodium issues here in a minute, but here's the sodium absorption ratio. That's one way to measure sodium, and it's probably pretty good. We'll look at that here in a minute. And then it also lists all of the, a lot of the nutrients that are listed here that are in the water. And then you'll notice it's kind of interesting. This column over here on the right shows pounds per acre inch. So if you're putting on irrigation, like for me, my plots on campus, we're doing 24 acre inches to maybe 30 a year, depending on the year. So you're going to multiply those numbers by about 30, and that's how much you're putting on. So like calcium, for example, you're getting, you take this number here and multiply that by 30, you're actually fertilizing with a lot of calcium just with your water. All right. So these formation of these saline and sodic soils, again, high precip areas, water's moving through, including the sodium, and it just moves out and ends up in the ocean. So it's usually not a problem in those areas. Saline and sodic soils and waters, they tend to form in arid and semi-arid regions, like here in Utah, most of the Western United States, obviously like places like Seattle, Portland, where it rains a lot, that's a different story, but most of the West is usually what we're talking about. Now, I have seen salt problems. I had a client in North Carolina that was using some reuse water and had a really significant salt problem. So definitely can be in other areas too, but that's usually a Western US issue. Now, sometimes the parent material, like that manko shell I showed you, could be high in the salts, but usually it is the irrigation water that's causing the salts to accumulate in the soil, and we've got to deal with them. Now, we also have saline sodic soils where I have both a sodium problem and a salt problem. So that's something that we can also have, and it's important when we're remediating that to try to do it in order. I'll show you that here in a few minutes. So again, measuring salinity, we measure it usually with electrical conductivity. By the way, labs will sometimes list it as electrical conductivity or just conductivity, like that Logan lab we just were looking at, or they might just say EC, or they might say soluble salts. I mean, they call it different things, but that's all kind of the same number, right? And we talked about why we measure it, electrical conductivity. So a high EC means high salts. In terms of measuring salinity, to be classified saline, again, it's above 4, that's technically saline. So, but again, realize that that's, sometimes we get into trouble with numbers less than 4, and that's soil. The water numbers are different. So a saline water, the number 4 doesn't apply. This is just for soil. Anyway, yeah, we kind of cover that. So measuring sodic soils, so most of the time we do not do that SAR. So the SAR is the sodium absorption ratio. The equations here. If I'm doing water testing, that they will oftentimes give me the SAR number in water, but on soils, I usually don't get the SAR unless I ask for it. And frankly, 99.9% of the time, you don't need it. But what you will get is this ESP, or this exchangeable sodium percentage. So if your lab is measuring pH, calcium, magnesium, sodium, and potassium, those 5, then they can calculate, or you can, but usually they do, this ESP number. And so we look at both of these in terms of soils, and usually the SAR for the water. So, and when I want to manage these things, if I have a saline soil or a sodic soil, the order of remediation is really pretty critical. I need to ensure that the drainage is there. Like, I got somewhere for the water to go. And if it's sodic, I add gypsum or some other calcium source that's soluble, not limestone. Limestone is not soluble at high pH, so don't do that. But I could use another calcium source as long as it's soluble in that pH. And then we need to leach the salts with good quality water, or as good a quality as we have. And sometimes we need to calculate a leaching fraction, and I don't have time to go over that today. I just have a limited time here, but usually I can get that from the lab, and there's some publications as well that I'll show you here in just a second. Here's out of a book that's with a focus on salts, kind of some things that, we sort of want in the normal range. And if anybody would like a copy of this, I'm happy to send it to you. But it's in this book here, Salt Affected Turfgrass Sites. It's a good book by Caro and Duncan. There's also a couple things that I've written up that are shorter, they're free. You can just download them. This Managing Salt Affected Soils for Crop Production. And I know it says crops, but the principles are the same. It doesn't matter whether it's potatoes or grass. I mean, we kind of do things the same. And so this is a, fairly short read and pretty friendly to a user. Here's another one. This is managing irrigation water quality. And I'm also an author on this, and it's also free online. So I just wanted to end up here though with sodium. It's a little complicated in water. The rest of it is kind of easier to deal with, but kind of just one number. Like the salts is, like if your salts in your soil are above 1.5, that's a number I can kind of latch on to. Yeah, we have numbers like that for boron and for chloride, and they're in those two documents that I just showed you. The sodium one's a little complicated though for water, because you have to look at two numbers. You have to look at the EC, the electrical conductivity, and the SAR. I'm not going to explain why that is the case, but you use a table like this. So like on that one we were just looking at with the Logan lab, so the SAR was pretty low. It was like 1, and the EC was also low. So even though they were both low, I actually have a high infiltration problem because they're both so low. If let's say that the salts were higher and I still had an SAR of 1, so I'm in this category right here, but my EC was above 0.7, I'm going to have a low risk of water infiltration problems due to sodium. So that's how you would interpret the water quality for this. I'm running out of time, and I waxed poetic too much, so I'm gonna stop. I got a few more things that I planning on kind of talking about, but I think I'll stop now and give some time for questions.
Thanks, Dr. Hopkins. If you guys have any questions, please enter those into that Q&A feature on your screen. Oh, we have a quiet bunch today.
Maybe I just did a really good job. Or I put them all to sleep, one of the two.
There we go. Stephen is asking, how much does drought affect salt levels in secondary water source?
Great question. It really depends on the situation, but it has the potential to. We certainly do see that, so you can see like especially surface water like lakes and those kinds of things, they can definitely become saltier with time, but even groundwater can gradually become saltier. Usually rivers are pretty fairly constant. I mean, we do see some difference, like even here in Utah, like the Provo River, for example, the salt concentrations in it are really not very high, and they kind of stay pretty much the same most of the year. They get a little bit higher towards the end of the summer. But like now, which like last summer, we're in the middle of this horrible drought. The EC values were slightly higher than non-drought years, but not massive. But again, the potential is, so it really depends on your water supply. Now, if you're using reuse water, and especially if you're starting to cut back on your water, then your soil is going to get saltier too. So your reuse water could end up getting saltier. So that's probably a bigger issue.
Okay. Donald is asking if you could please show the chart from a couple slides back.
Sure. Let's see. Oops, I think I scrolled down accidentally. I got 1,000 slides. This chart?
I'm not sure yet. We'll come back to this. Okay. Nick is asking, how often should well water be tested?
Yeah, good question. Well water typically doesn't change too much over time. Like my family's farm, we're testing, we probably should do it more, but we're testing like 3 to 5 years. And it doesn't really change much in that time in some of these deep wells. Now, some shallow wells, they can change more, and certainly surface water can change, monthly. So I usually say, well, you probably ought to test every year. Just to kind of keep an eye on it and track it yearly is a good answer. But there's a few places that I work with that we have to test like every month because it's a moving target.
Okay. Don is asking, for those who may use reclaimed water to temporarily cool synthetic turf, is there an impact on Gmax ratings?
I doubt it, but I don't know for sure. I don't know that I've ever heard anything in that, but I just understanding chemistry the way I do, I can't see why it would affect it at all. Yeah. Hey, another thing just popped in my head though, unrelated to that question, but I just wanted to mention, I'm not endorsing Logan Labs. There are a lot of labs out there. We have a lab here at BYU that I use a lot. There's a whole bunch of labs out there, and if you are, in fact, I have a website I can point you to kind of, you can go find a local lab. So anyway, I wanted to make sure I said that.
All right. Where can you purchase a water testing kit?
You usually don't need to purchase a kit. You can contact the lab and they will typically give you instructions, and many of them will actually send you the containers. For testing irrigation water, you don't really need anything fancy. If you're testing the water in your home for like E. coli, bacterial stuff, then you definitely need to reach out to the lab and get their specific containers. But if you just find a plastic container that's clean, that's good enough, and you can send it to the lab. They need about a pint of water, maybe a quart. Don't send it in glass. If you got a really nasty, like if you're using like swine effluent, something that's really got a lot of organics in it, then you probably got to call the lab and get some instructions. But normally you just go buy a plastic bottle somewhere.
Okay. And related to that same question, he said they're testing reclaimed water used for irrigation.
Yeah, most reclaimed water is going to be fine just to put it in a clean plastic container, at least a pint to a quart. Don't send them a gallon, that's too much.
And then in regards to the chart, he said it was actually a table and a slide you said that you could get to us. It's about 1 to 2 slides previous to the one being shown.
This guy? I assume this is the one. Yeah, this is the one I said that for, so I'm pretty sure that's what he's saying.
Okay. Next question. Cations on a test result for soil. What is the optimal result and what does it mean?
So that's another really commonly misunderstood. And I deal with this all the time, and I get a lot of people arguing with me, but I would suggest that the science backs up what I have to say. And we have a lot of data on this, is that those percentages, other than sodium, are meaningless in terms of fertilizer applications. So when I'm fertilizing, so potassium, calcium, magnesium, if I'm considering those, I ignore the percentages and I just look at the concentrations on the soil test. But sodium, it's just the opposite. I don't care about the concentration. The concentration is used to make the calculation, but for sodium, I need the percentage. That's the exchangeable sodium percentage, and that number is important for sodium hazard. So that's, and again, we got a lot of folks in the world who believe the opposite of what I just said, but I think if you talk to most turf grass professionals who are scientists who understand the data, like Nick Christian's, for example, in his textbook, or in any of the common textbooks, they're going to agree with what I just said, because the data just says that's don't manage your fertilizer with percentages, manage your sodium with percentage.
All right, where should we test the water, from irrigation or at the pump?
Yeah, that's a convenience factor sometimes, because like on our farm, for example, it's just way easier to take the sample. So we turn on, like, we'll turn the pump on and we'll let it run for a little while to make sure that I've got, I'm not getting just something, left over, from the pipes or whatever. But so we'll usually sample from the pump, but technically you probably should be sampling from the, where it's, from the emitters, or from the sprinkler heads. But either way is fine as long as you let the water run.
All right. Do you see or have you seen positive effects of using hydrogen peroxide products to treat a water source or a soil?
No, is the short answer. And there's been some studies, and hydrogen peroxide, as soon as it hits the water, it's water. You're wasting your money. And again, I have some folks who I know and respect even that believe otherwise, but I like the statement that I say a lot. In God we trust, all others bring data, and the data I've seen just says no. Now, I will say, in terms of treating water, one thing that I do like to do, I just didn't get a chance to talk about it too much or at all, is acidifying, water. Water tends to be hard. It's got these carbonates in it. That's not really, they're really not really great. They tend to put stains on our buildings and clog up our drip emitters and those kinds of things. But they also plug up our soil pores. And so it's kind of expensive. It's not for everybody to, but if you've got a, kind of a high-end property, I really like injecting a little bit of acid, not too much. I like sulfuric acid or a sulfur burner, even better, so I don't have to handle the acid. And I don't want to overdo it, right? I don't want to get it so acid it kills everything, but that's really a nice thing because it just takes that carbonates out. And I can even use, if I use the right blend of acids, I can even put my fertilizer on that way. It's a pretty slick system. It's complicated. If you're ever going to do that, you probably ought to contact an expert and make sure you're going to do that right. But if you're going to treat water, that's what I would do.
All right. Well, we don't have any other questions. If you guys think of anything, feel free to reach out to Dr. Hopkins with those questions. So thank you all for joining us today. We do have another presentation that starts at 3:15 Eastern Time. That presentation will be data and decisions applying research in sports field management practices. So make sure to register and join us for that presentation in a few minutes. Thank you, Dr. Hopkins. Thank you, everyone, and have a good rest of the week.